Well, this is not about what we heard before, policies for workflows. This is just singular. It is a workflow. And well, I can tell you there's one thing that you missed in the policy. The stress factor of a live demonstration of a workflow should be included. Yeah, exactly. Especially of the one who has to give it. So what this is about engineering design workflows. And there we are working together with Surf and Theo Viana for quite some time now. And I think this is maturing more and more. And let's say with every technology step that we make, we also figure out we have to also take on the engineers. While talking about the engineers or engineering design, what is it? Well, it can be anything. Yeah, it can be a gas turbine. It can be a ship hull or a ship interior. It can be this Millennium Bridge that we saw already in the previous talk. Yeah, basically, we are not yet at the stage that we could replace a CATIA or a commercial software for the one or the other. It's more we're developing the methods, we are developing the workflow, and now we are at the process to connect this with the people who ideally have to use it at the end of the day, and then getting feedback into, yeah, is this usable? What added value does this new workflow give? And yeah, will it be accepted? And when we talk about engineering design workflows, yeah, so here I took two mock-ups. The one is from Microsoft, the other from Siemens. It is basically about, yeah, designing some engineering product, whatever it is, yeah, from the slide before, and design it on a computer, analyze how the performance will be, optimize the performance, but there it doesn't end, yeah? So typically then you fabricate the product, and this product has a lifetime of several years. And it's not like this product lives in isolation without maintenance. Yeah, and ideally, you want to have a so-called digital twin that is kind of accompanying your real-world product, and then you can do, let's say, maintenance planning. Yeah, for example, think of an airplane turbine. Yeah, this is very much, let's say, standardized what has to be done, and if these turbine blades have to be replaced, yeah, you want to analyze this digitally before the airplane comes in. Yeah, so it's kind of this digital twin lives together with your real world product. Okay, let's make it very simple. Yeah, there are basically two big components. The one is the CAD, the computer aided design. Yeah, and here I take a very simple bridge because that is overseeable. An airplane engine is a bit much more complicated. Yeah, and then there is I call it computer aided engineering. You could call it analysis, optimization, etc. Yeah, so it's basically the design, and design, it's already in the name, I would say, is something that has to be done interactively. Yeah, some people or some human designer at the moment is interactively making this design on a computer, and that starts to change, but it's mostly still that way. Another human, yeah, because they come from different disciplines, does the analysis, and that is not really interactive because these are typically heavy computes. This is more in batch mode. Yeah, so things start to change, because new compute facilities or new compute capabilities are coming up, but also there are, yeah, I called it new kids are on the block. AI is everywhere. Yeah, for example, have you heard about this Zoo text to cut? It's amazing. I mean, it does not yet beat a human designer, but it's interesting that you just can type or with speech recognition say, please design for me this or that. And it gives you some design which, well, looks pretty good. Or, well, NASA demonstrated this with generative AI, that you can really come up with very, let's say, nature-inspired shapes, yeah, that are really now fabricated and used. Yeah, and AI is everywhere. So also on the computational side or on the simulation side, we have reduced order models, we have physics-informed machine learning, data-driven models. And well, what shifts there is from just batch mode, long-term computations, to interactive. Yeah, so you have an offline phase where you train the whatever AI thing, and then you have an online phase where you can instantaneously evaluate it. And actually this fact that the simulation does not become so time consuming anymore, at least at the moment you need it, makes a lot of things possible that haven't been possible before. Yeah, because you can do interactive design and analysis, not just interactive design. Okay, with all this, because all of these different topics have kind of legacy, comes the incompatibility challenge. Let's start here. So CAD, since 50 years, uses NURBS, kind of a spline type thing. And when you look here, I hope you can see it, NURBS just have to, or let's say CAD designs just have to look nice. They don't have to be correct. What I mean by that is there are gaps. Yeah. So at this part of your hand, there's a little gap with this green box. This isn't a problem. It looks nice, but analysis would completely fail there. Second thing is you just have hollow models. Yeah, you just want to see from outside how it would look like. Analysis, unless it's a shell, means you have to go inside. You want to see what happens in my hand or in my bridge or in my whatever. Yeah, and that is, well, I took this picture, which is already 25 years old now, but it hasn't changed since then. Basically means when you come with a cut geometry, it takes literally a lot of manual work to make it into a useful geometry for the analysis. Yeah, and you see like the analysis, solid model creation, geometry, decomposition, meshing. Yeah, these are the big chunks of the work. And surprisingly, it's not really the run-off simulation. That's 4%. Yeah, put a big HPC system, it goes overnight. Yeah, it's this preparatory work that kind of makes the big problem. And then if you now think about, well, if we have run one simulation, we want to feedback the result and improve the design, it's incompatible. Yeah, so I hope you can see this Stanford bunny is a nice geometry model at the beginning. It's just an approximated mesh at the ends, and there is no link back because you broke with the geometry. Okay, now if the new kids on the blocks come in, yeah, it gets even worse because, well, these text to cuts, they look nice, but actually many of them don't even generate parametric models. They just generate point clouds, which from the aesthetic aspect is enough, but for an analysis, it is worthless unless you can recover a geometric model. And the same here on the other side, the physics-informed machine learning, they are completely different in the way they predict solutions. So no engineer would trust them right away. Yeah, you have to bridge the gap to the good old known, let's say, finite element, finite volume stuff that has, let's say, theory behind and trust behind it. Okay, then there was 25-ish years ago this attempt, let's unify CAD and finite elements, and we called it, or they called it, the initiators isogeometric analysis. So this is really literally taken from the book of IGA. The problem is technology doesn't solve the problem alone. And because if we look at, well, what was the way to do? They said, don't take a grid and a geometry, but take the same mathematical language, NURBS, for both. But the challenges remain. Yeah, so there's a hollow surface or a hollow shape is a hollow shape and won't be a volumetric one. Yeah, so you really have to change the way the design is done. Yeah, go to volumetric cut. If you have volumetric cut, the designers that are kind of used to B-reps, surface ones, won't accept it unless you automize a lot of the things underneath. Yeah, you want to modify the outer shape. Don't want to care about the million grid points in the inside. Okay, then if you have this, you also have to say, if you have your designers on board, you also have to get your engineers on board, because what is the added value of this thing? Yeah, so this design through analysis workflow, and well, then the last step, integrate AI. And what we did a couple of, well, actually, some 2 years ago, it started with the help of SURF, or with the intensive help of SURF, I would say. We started this DTA tools, an interactive and collaborative design through analysis workflow, and that's workflow here is the key thing. The vision we had at that time was, well, we have a front end where with any device you can think of, you can connect. You have the back end that does the computation. Well, then in practice, we saw, reality check, if all these devices show you exactly the same thing, no one will accept it because, well, on the right, this is VR. I brought the VR if you want to test it in the break. Yeah, so it doesn't have added value if you use it as a replacement for your 2D screen. Yeah, you have to do something extra. Yeah, and I recorded it yesterday. Designing interactively and looking into your design might be much more helpful in VR, whereas, let's say, looking at the quality of your, that's on the left, of your geometry can still be done in 2D. Yeah, you have to find the right kind of use of the capability of the device. Then accuracy versus responsiveness, and here comes the AI in. Yeah, so this is very simple. 2D linear elasticity, you're fixing it on the left and pulling a sheet, and then it deforms, and this is the stress. Yeah, so on the left, this is the simulation that takes long. Well, this is 2D, it takes a minute maybe, but it takes, in the perspective, long, whereas this, after a day of training maybe, can do it in milliseconds. Yeah, so, and it's visually accurate. Of course, it's not as accurate as the true calculation. And now, if you're putting all this together, this is a little bit showing the setup that we have now, and this is really working. You can go there and play with it. If I have time left, I will also do it live. Yeah, and the idea is that at some point in time, also an AI agent is kind of complementing the human team. Yeah, because an AI agent can also generate designs, which are then kind of treated as equal suggestions between the team members. And the last thing I want to touch is deployment. At the moment, these are just 2 Docker containers. Works very well for testing and for showing it. But, well, at some point in time, the compute part will just, yeah, kind of not be doable in the Docker anymore. And that's something that's the work in progress thing we are doing now, is deploy this with the entire surf infrastructure. So that means authentication has to be done. And then, well, the compute has to be done on Snellius, how to exchange the data, let's say, how to trigger the compute job, how to get the data back. These are all solved problems, but they have to be implemented, and they have to be implemented in a way that once it runs on Surf, it maybe also runs on Lumi or another HPC infrastructure. So a lot of technical problems, and I don't want to steal more time. I think the last point, the 4th bullet point, is the one that is important: usability. So we can prepare, of course, whatever we think is great, but at some point in time, the end users have to tell us, this is okay, this is crap, but if you change it like this, we are willing to use it. So I think part of the workflow is the human. Thank you.